Today, I would like to introduce the most easy to understand structure, yeah, flash ADC. But also, there's some innovation inside such kind of very simple structure. Well, let me just show you that this is the most, how can I say, the fattest ADC structure here now. Oh. You can see it adopts such kind of parallel conversion because the input is compared to all the quantization levels. Yeah, and how to generate such kind of quantization levels? Usually through voltage division. Okay, but this is in voltage domain. If you do such kind of conversion in current domain, then you need to have a current division. Yeah, current sharing, blah, blah, blah. Or the so-called current steering. Anyway, this is the so-called comparator. To compare the input to each quantization level, we need a converter. But from the structure, you can see the converter is composed of two amplifiers. We have pre-amplifiers and finally the real comparator. But why? In the past, actually, we only compare, this is two level, right? Then positive, negative, V in or positive, I don't care. Okay, we have only one comparator, but for real, that is in theory. For real implementation, actually, this is a better way, yeah, to have not only comparator, but a preamplifier. Why? Two major reasons. First of all, let us explain the second. But first of all, with such kind of preamplifier, then we can reduce the impact of the input offset voltage for comparator. Okay? Yeah, that is so-called VOS. If you have only one stage, it means the gain needs to be much higher than the current structure. Much higher gain usually means you need to sacrifice all the others. Yeah, the input offset voltage, blah, 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 everything, stability, right? So, for example, if you need 1,000 for this comparator, then maybe we have 10 here and 100 for the final comparator. Yeah, in this way, we can achieve the same gain, but we can reduce the impact of VOS, comparator input offset voltage. Why? Okay. For example, if you look at from here to there, from input to output of the preamplifier, it is an amplifier, so it means Vin will be amplified. You will get some gain from the input to the output. But on the contrary, if you look at from here to there, I mean from output to input, you will have the so-called attenuator, right? 从输入看输出，它是放大；倒过来看，它是缩减。What I'm talking about is, hey, we have VOS for your comparator, but from here back to there for the preamplifier, then the VOS of comparator will be attenuated. That's it. Okay? That is the first reason why we need to have such kind of structure, preamplifier and comparator for real implementation. And this is something not mentioned in your microelectronics or even in many of the analog IC design textbooks. Yeah, hopefully you will pay much attention to such kind of detail to make your flash converter, flash ADC, as good as possible. And then, to explain the second reason for such kind of structure, yeah, we had better to know because for such kind of preamplifier, you can see it has two input and two output, right? So it is the so-called fully differential. For fully differential one, the transfer characteristic curve needs to look like this. This is for positive, but this, yeah, because we have how can I say? For our free differential structure, right? I think you already know that this is your positive input, then that is positive output, right? This is your positive negative input, then negative output there. They are contradict to each other. From here to there, positive to negative. From here to there, negative to positive. Got it? So the transfer curve look like this. And then if everything is perfect, okay, so to make the output of comparator become 1 over 0, right? What is the threshold voltage for this one? If the comparator is perfect. Oh, because this is for the input to the output, for the input to the output, right? So actually the comparator compare the output of this, okay? So the output, maybe this is VO plus, that is VO minus for preamplifier. Actually, they are connected to two inputs of the comparator. So to make the output become 1 or 0, it depends here, okay? If I am larger than you, the purple line is larger than the green line, you get 1. On the contrary, you get 0. Got it? So for such kind of comparison, yeah, the so-called threshold voltage is actually here. In the middle, I mean, for the cross point. Right? This is the real threshold voltage for comparison. Why I'm talking about this? Maybe for some students here or for some new engineers here, a piece of cake. Why I need to spend quite many minutes to explain it? Because for the next, we would like to reduce the complexity of the overall structure. Anyway, before I explain the second reason, yeah, you need to know that the complexity of the structure actually is increased exponentially with the number of bits. And it means for each bit, for each extra bit, the structure will be complicated by 2 times. For 2 bits, 4 times, 3 bits, 8 times. Yeah, 2 to nth power. So it will increase the so-called exponentially, the number of bits and the complexity of the overall structure. That is real money wasting, area, power wasting. Okay, so this is the typical performance. 4 to why 4? For very high frequency operation, gigahertz, tens of gigahertz. Under such kind of very high operation frequency, usually maybe sometimes only 3 bits. Okay, yeah, and then for a little bit low frequency, maybe hundreds of megahertz operation, possibly for 10 to 12 bits. Anyway, upper frequency, yeah, this is in the pace right now, gigahertz or tens of gigahertz, according to the process evolution. Anyway, high power, large area, yeah, high cost, yeah, and also that the other issue is for the input. It needs to be connected to all those preamplifiers. Oh, that is another reason. Okay, and it needs to be connected to the input of the preamplifier, so it gets a lot of input capacitance. Okay, so it means what? It will slow down the operation. To speed it up, you need to have large driver to charge or discharge the parasitic capacitance. Again, it will waste your power and also area. Okay, so how to solve it? Again, such kind of structure is better than only one comparator. Why? Because as I mentioned here and there. For preamplifier, the gain is much smaller than the comparator, even smaller than a single comparator. For a single comparator, you need 1,000. But right now, for preamplifier, you only need 10. 10 compared to 1,000, it means 100 times reduction in gain. Also means that almost I cannot say 100 times, but maybe 2 order area reduction from the single comparator to preamplifier. It means the parasitic capacitance here will be substantially reduced. I mean, compared to the traditional structure with a single comparator or without any preamplifier. That is second reason. So for that, I have the third reason. Yeah. From the beginning, I told you I have 2 reasons. No, 3 reasons. But later, okay? Anyway, the other issue to remind you is how to generate good enough quantization levels for all of them. Okay, you need to match each resistor to all the others. But how? Allow me to show you this. Here now, that is the best structure on Earth to match so many critical devices. All right. If you read all the layout papers here now, yeah, for systematic pattern generation to match critical devices, if you would like to match more than second order, okay, this is only good for second order. Okay. For multiple critical devices, multiple means more than 2. Okay. For more than 2 devices, then sorry for that, you can only match their properties to the second order. That's it, no more. If you would like to match more than second order of mismatch, okay, then yeah, for all the papers, you can only match 2 devices. All right? So you have 1, 2, 2, 1. Okay, this can help you to match the first order, and then 2, 1, 1, 2, the second order, and then you flip it to 1, 1, 2, 2, 1, 2, 1, 1, 2. Configuration, you can match the up to the third order, to the first, to the fifth. We have a systematic way. That is what I'm talking about. A systematic way, 一个系统性的做法 to match for more than 2 devices, only up to the second order mismatch. If you would like to match more than second order, sorry for that, only for 2 devices. Okay, so it means for more than 2 devices, for more than the second order, nothing existed on Earth. All right, 要匹配超过2个元件，同时要能够消除2次误差的话，拍谁不会做物件。Okay, allow me to show you this. You can see, for example, R0 here. Okay, this is for the first half, and then how about the second half? You just flip it. Okay, I mean, you have some kind of mirroring layout pattern. Yeah, this is the mirroring axis. To the left, to the right, to the top, to the right. I don't care. Okay. Anyway, allow me to show you the first order one. R0 here. Okay. So where is the centroid for all those R0 resistors in the middle? And how about R2? Oh, the same. 2 here, 2 there. So here and there, in the middle. Bingo. Okay. And how about R1? The same. Okay, you can do it by yourself. All right. So it means what? Configurations. Here we have the so-called common centroid layout. For common centroid layout, we can promise you, we can cancel the first order of mismatch. Okay, and then, but before that, we call it diagonally shuffle layout. Diagonally, 对角线的 shuffle. Look, yeah, they all look like this way. and to the other pattern, they all look like that way, right? So that is the so-called shuffle pattern, okay? But in the diagonally way, so we call it diagonally shuffle layout pattern. And then that is for the previous paper. For this paper, they have another idea called mirrored, okay? Because for the diagonally shuffled pattern, they can only cancel the first order mismatch. To increase to the second order, they're fine to do such kind of mirroring. Yeah. And then one to the right, to the left, to the top, to the bottom. Yeah, you will get the same power of second order mismatch cancellation. Yeah, so you can see, you have the so-called V shape. This is for R0, right? And then R1, R2, R3. Anyway. Yeah. To help you more, anyway, okay. If you are interested, please read the paper by yourself. Yeah. And then, because it is related to IC layout, but I don't have enough time to teach you everything for analog IC. So you had better read it by yourself. Yeah, you just Google online the keywords. Yeah, mirrored shuffle layout. Yeah, especially through i3 Explorer, you will get the paper, exact paper. If you have any problem with that, just contact me. I will offer you the paper, the name of the paper, or even the PDF. Anyway, we can make this overall structure even better than before, okay, by such kind of interpolation. Yeah. We would like to reduce briefly, 50% of the preamplifiers off. 50% off means what? Less area, less power, and again, less input parasitic capacitance to speed up the overall operation. Yeah, but how? How to steer 50% of the preamplifiers? Yeah, 要如何偷走50% 的 preamplifier? Okay. Again, please pay attention to this. For the amplifier, it needs to have something like this, and then the threshold voltage for comparison is in the middle. Got it? Got it? Okay, let's go further here. Yeah, it is quite interesting. Okay. For example, for this one, you would like to steal it, to delete it from the overall structure. But you'll be curious, hey, I have no preamplifier. How to compare my input? Where will be my input? Oh, you can also steal the input, borrow the input from your neighbors. 你可以从你的邻居，因为你没有前面的前置放大器，所以你从邻居去借你的比较讯号。Okay, that is what I would like to tell you. Yeah, for example, to my top. Here, that is for the top. The red line and the dashed blue line. Why it is to the top? Because the threshold voltage to my top neighbor, right? It is here, VR2. Okay? And how about my bottom neighbor? Here. VR1. Okay? So for VR1, it has the solid blue line and the dashed red line. Red for positive, blue for negative. Okay? I mean for output. Got it? And then, but I borrow both dash lines. Okay? Blue dash line from my top neighbor. Yeah, and red dash line from my bottom neighbor. Yeah, I got. Please pay attention to two dash lines. So I am the comparator. Which is my threshold voltage? Again, the cross point. Right? You can see the cross point, the threshold voltage here, actually it is in between of VR1 and VR2. If they are symmetrical to each other, to the top, to the bottom, VR1, 2 will be this plus that divided by 2, the average voltage between VR1 and VR2. That is exactly what we need for this one. So even without preamplifier, I can still survive through the help of my neighbors. Got it? That's it. So you can see the overall structure look like this. You have preamplifier? No, yes, no, yes, no, yes, no. So in theory, you can steal total 50% of the preamplifier. Wow. Then also, we have the other way for such kind of structure. We have the other way to improve the TNL, because I got the average of those two, right? Maybe this is for ideal case, but for real case, yeah, maybe you will get positive, negative, negative, positive. Congratulations, you will get better VR1, 2. All right, got it? Yeah, because nothing is perfect, even for the resistors. You apply such kind of very complicated layout to match all of them, but there is still some mismatch, random mismatch. Okay, so for random, this is positive, negative, positive. Oh, who knows? Maybe you will argue that, 50% of the probability is positive, positive, negative, negative. Okay, you can still improve the reduce the error for VR1, 2. Why? Okay, you can see for VR2, if you are so unlucky, you get the maximum for mismatch. All right, but how about this one? The probability for VR1 to get, even it is also positive, but to get the same positive Vmax, the probability is almost 0. Okay, so even though you get one maximum, but for the other one, it is more likely not maximum, even they have the same positive or negative polarity. So as an averaging, VR2 is still less than this. I mean, for error, for inaccuracy. So in this way, we can improve that kind of DNL for this one. Okay, that's it. Yeah. And then to reduce the power and also the chip area, actually you don't need to apply very typical structure for such kind of comparator, because it is power and area consuming. So allow me to show. Yeah, especially for very high operation, very high speed operation. Usually, we try to not use such kind of static structure, because static comparator, static something, usually means it consumes power even without any operation. So we can go for dynamic operation. This is one of them. Yeah, dynamic. One of the dynamic comparators. We call it clocked comparator. Okay. Yeah. So you can see the overall structure look like this. From the beginning, you can put the VOS of such kind of inverter on the capacitor. Yeah, that is for the so-called auto zeroing. Okay. Yeah. Anyway. Yeah. But right now, for auto zeroing, I will explain later. Right now, I would like to tell you how to do such kind of, because you need to know the difference between your Vin and your reference voltage, and then check it is positive or negative, right? To get 1 for positive, 0 for negative, blah, blah, blah. So how to get the subtraction between all those? Okay, allow me to show you. From the very beginning, you can see we connected Yeah. You grounded the other terminal, okay, and short here. It means transmission gate. Yeah, it looks like an analog switch. So when you close it to the ground, and then but not only ground but also the VOS on C. Okay, yeah, forget about it. It will become too complicated. So right now I would like to explain how to get the difference between V in and the reference voltage or the quantization level you would like to compare with your V in. From the beginning, grounded. Okay, then yeah, you put V in here, VRI here. Okay, and then open it and then connect it to V in. Haha. But I told you already, for the first moment, we put VRI here, right? Right? So when you cut off all the leakage paths, yeah, open it, you open, there's no way to charge or discharge the capacitor. And then you connect it here to V in. But you still get positive, negative, I mean the terminal voltage for the capacitor is still VRI, right? Okay, so what is the real voltage here? It should become V in minus VRI. Because I minus U, I get VRI. Got it? That's it. Congratulations. You can compare the final voltage to be compared. Look like this. All right? Yeah, just like this. Okay, like it. And this is a single stage inverter. I told you already. I explained already. That is the so-called high gain stage. Okay. Yeah. Usually the gain can be as high as 2 orders. Yeah, up to 100. Anyway. Okay. That is a very, very easy to understand structure for you. Yeah, but this is only for explanation, for you to get easy understanding about such kind of clocked comparator. Because for the positive, negative, yeah, this is to charge capacitor to VRI, and that is to get V in minus VI, blah blah blah. Okay, we need the help of clock. Okay, and also non-overlapped clocking. It means the operation of the switches, they cannot be overlapped. So usually you need to have, this is for phi 1 here and there, okay? And that is for phi 2, 1 and 2. They cannot be overlapped. It means the switches cannot be turned on at the same time. No. You need to have some kind of time zone for all those switches are off. Everybody is off. Okay, so that is the so-called non-overlapped or non-overlapping clock signals， 非重叠的时脉讯号。啊，一定要有一段时间是所有人都给我闭嘴，因为我们很怕重叠。If there's some kind of overlapping, it will cause a big trouble for such kind of operation. Anyway, that is only for your goodness, for you to get better understanding. But that is only single-ended operation, right? Usually, we need full differential inverter. Okay? And then, for the design of such kind of flash ADC, for INL, usually it looks like this. Okay? Not exactly, okay, but where will be the maximum INL error? Okay, usually in the middle. Yeah, if some of my students design ADC or DAC, especially for minor weighted structure, blah blah blah, you can see if you have INL simulation results, you will see usually you have the maximum in the middle. Then oh okay, that is 50%. Okay, yeah. Anyway, and that is for the second largest usually 3/4 or 1/4. Okay, this is dominated by MSB. Okay, and this and that, yeah, are dominated by the second MSB bit. Anyhow, that is the usual case. Okay, in the middle, usually you get the maximum INL. That is really harmful. How to make it? We can do calibration to make it like this. What do I mean calibration? You have some kind of reference, exactly reference voltage. In the middle, you get the maximum, usually in theory or in practice, you get the maximum deviation for your reference voltages. Okay, the maximum usually is in the middle. So how to solve the problem? For example, 0 and V reference, right? You need the help of V reference by 2. Ideal 50% of the V reference and connect the ideal voltage source to the midpoint. That's it. It means what? It secures in the middle because the middle is connected to the ideal voltage source. No error for that. Got it? Okay, that's it. So you can reduce the angle to that. No error here. Configuration. And how much you can reduce the angle? If you overlap it, then it looks like this. Usually 50% off for your angle. Okay, hey, we can do the same thing to reduce it further. Doing. Yeah. But right now you need the help of V reference by 4 and 3/4 of your V reference. Okay, nothing is free. You need to pay for it. That is, I need to point out another ugly truth according to the papers. For many of the papers, they simply tell you, I would like to do such kind of calibration. Okay, so for their measurement, they can really make it like this, or even better like that. But my question is, who provides such kind of reference voltage for a circuit? Usually, they don't have that kind of reference voltage on chip. No. They do it off chip. Okay? And it means that they push their responsibility to the others. Somebody needs to do something for the chip. Yeah, somebody needs to provide this and that reference voltage for the chip. They don't do it. Okay, and how to measure it? They have many kind of very luxury power supply to generate all the powers they need. To be honest, that is only for academia papers, not for the industry. Because for the industry, nothing can be off chip. If you need to do it by yourself. But to generate such kind of perfect voltage sources, it means you need a lot of chip area, power, and design effort. Okay? So usually that is not a good way to compare this and that. No. To compare apple to orange, orange to apple. That is the usual case. Many of the authors, they have such kind of very embarrassing condition. They only say, hey, to save power, to blah, blah, blah. So they need to have this, and that supply voltage, but they never design it. Okay, they never mention about how to generate it. They suppose everything they required existed already, but it is usually not true. Okay, so if you read the papers, you need to be very, very careful. Don't be cheated. Okay, they try to cheat you. That is what I need to warn you. Yeah. Anyway, from the very beginning, I tell you there is some kind of sampling window, yeah, jitter, blah blah blah, yeah, clock skew. Okay. Skew means what? In Chinese, we call it 歪斜. Anyway, they are not aligned to each other because your clock signal look like this, okay, a periodic one. So again, on the screen of your oscilloscope, this edge, and that edge needs to be fully overlapped. But that is only in theory. In practice, you have jitter. They are not aligned to each other, so you will get such kind of clock skew. Okay. Not only for jitter, but also for routing. If you go back to the overall structure, wow, how to make the arrival of all your signals, because you need to connect this to all of them, and then to, yeah, all of them. How to make sure all the signals arrive at the same time? No, sorry for that. Sorry. During layout, you can try to match them, right? If the delay is shorter here, then you can do more complicated routing to expand or to have some kind of parasitic, yeah, to get longer delay, blah blah blah. Yeah, you can try your very best to match the arrival times of all the signals, all the inputs for your positive, negative, complementary input. Anyway, anyhow, after fabrication, you still have clock skew. Okay, not only for the input signals, but also for clock signal. Yeah, because for high-speed operation, we have such kind of clock comparator. You need the help of clocks. Okay, so to turn it on, to turn it off, blah blah blah. How to align all of that? No, no, you cannot. You have such kind of clock skew. Okay, so you will get more errors because if somebody is not ready and you do such kind of clock comparator, blah blah blah, everything, yeah, you will destroy. You will sample, because I told you already. You need to sample VRI first and then V in second to get such kind of V in. Sorry, input minus VR in. What I'm talking. V in minus VRI. Okay. That's it. Right. So if the clock doesn't behave like what you think, it is delayed a little bit or arrive earlier, you will get the wrong sample because V in is not DC. V in is still changing. Okay, you get the sample here, you get the sample there, you will get some kind of voltage difference, blah blah blah. Then you will cause some error. Okay, anyway. So to reduce all these errors, yeah, first of all, to make the input stable, you need sample and hold. Okay. After sample, because this is the V in, after sample and hold, it will become flat, right? So for your clock comparator, you sample here, you sample there, you still get the same input value, yeah, to reduce such kind of error according to clock skew. Yeah, and also that your clock and your input signal should be routed together. What do I mean? Because you have so many inputs to be routed to such kind of many comparators. Okay? So, in brief, you need to match the routing between your input and your clock. That's it. Okay? For this stage, if input arrive later, then hopefully your clock is also arrive later. Yeah, it is shifted to the left, to the right. or it arrived earlier, then we shift both input and clock signals to the left, okay, to match all of them. Yeah. Anyway, that is very important for your real design. All right? And also, the background noise, yeah, just like the subtract, you get a lot of noise. All right. So this is another example. Yeah. If the noise injection according to your subtract, because subtract is really noisy, right? For example, yeah, 7.8 millivolt, yeah, for video reference 2 volts, 8-bit converter, it will cause you 1 RSB. But in theory, we hope we can control the error below 50%. Yeah, half LSB. All right. So it means that you need to reduce your subtract noise to 3.9 or almost 4 millivolts. Is it easy to do? No. Yeah. Sometimes for higher frequency operation, you will get more subtract noise because you need to turn on, turn off many of the switches on the chip, right? You get a lot of noise to interference with each other. So it's really hard, to be honest. Okay, it's difficult to keep such kind of subtract power supply noise less than this. Okay. Anyway, how to handle such kind of problem? Again, differential operation. Okay. For example, for your input and output, for your positive input and negative output, if you sample at the same time, you get the same inference from your noise, from your interference. Okay, then they can cancel each other. Yeah, in theory. Yeah. And also that you need to decouple your analog part from your digital. So it means for your chip, you have analog VDD, and you need to have digital VDD. Analog ground, digital ground, they need to be separated. Okay, and also that for guard rings needs to be supplied by your VDD by your ground, so you need to have VDD guard ring. It means what? For each good chip, it has quite many pins for VDD, quite many pins for ground. Okay, under such kind of very good consideration, you can achieve as good as possible performance. If you don't pay attention to such kind of detail, forget about it. The final measurement will be really, really awful. 如果你没有注意细节的话，不管设计或布局，你的量测结果绝对是非常的惨。This is the reason why you cannot compare your post simulation to the measurement result of the other papers. Okay, days ago, one of the paper was rejected by me because I served as associate editors for 2 IEEE journals. Yeah, the better one is TVLSI. Okay, IEEE transactions on very large scale integration systems or something. Anyway, it includes not only digital circuit but also analog circuit. In the past, TVLSI only focused on digital part. So since 2013, I was invited to be one of the AEs. Why? Because they would like to expand from not only digital but also analog. Okay, so under such kind of situation, yeah, I was invited. Until now, I still serve as one of the associate editors. Anyway, days ago, I rejected one paper because it compares its own post simulation to the measurement result of the other previous papers. Yeah, all the reviewers says it is unfair. Okay, never mind how good you are for your post simulation. Usually, it is never be true. After measurement, you get a lot of noise, a lot of interference, class skew, blah, blah, everything. Mismatch. Okay? So, lesson 1, don't compare your process simulation to the others' measurement results. It is really, really unfair. And the other one to remind you, on chip decoupling capacitor. It is really important because one of my students major, not here, one of the TA, he got the chip and days ago he measured the oscillator. Yeah, it works, but with some noises on the oscilloscope. He saw something like this. Wow, I was amazed. Do you have such kind of on-chip decoupling capacitor? I thought the answer is no. Okay, I didn't get the exact answer because Tony told me he forgot. He has no idea. Oh, okay. He has no idea means he didn't do such kind of on-chip decoupling capacitor. That's it. Okay. Yeah, but to be honest, his oscillator actually doesn't consume too much power. I was curious. Even without the decoupling on-chip decoupling capacitor, I don't think it will get such kind of noise. But anyway, yeah, do your very best. Okay, not only for the authors of the papers, even for my students. If they don't pay attention to all the details, something will go wrong for the final measurement. Or even you get some stone. It means the chip doesn't work. All right, it is really unlucky. But to make it functional, to get the best performance, you need to pay attention to all the details, never mind for design or for layout. So what I'm talking about for on-chip decoupling capacitor, I'm telling this. That is the overall IC, but the bell die is in the middle. We have many kind of bonding wire, okay, and then the metal pin. Usually, for you guys, deep with the easiest. Okay, such kind of package, dual inline packaging or something. Okay, 2排的那个封装. Yeah, deep packaging is the easiest, is the most convenient for measurement, but it gets a lot of parasitic capacitance, parasitic inductance, blah, blah, blah. So usually, if you are good engineers for testing between your VDD and your ground, okay, there will be some off-chip decoupling capacitor to stabilize the VDD and the ground, to absorb the noise on the VDD on the ground. Okay, that's it. But after that, how about your on-chip voltage? Yeah, again, I tell you already how to connect your VDD or ground to your on-chip, to your bell die. You need metal pins, okay, and then bonding wire L, yeah, and you have inductor, you have capacitor. So even the off-chip supply voltages are stabilized. Forget blocked because you have clock signal to turn it on, turn it off, blah, blah, blah. You get a lot of noise on chip. Yeah. So again, on chip, you need to have your own capacitors to do such kind of decoupling. Got it? Not only off chip, between your VDD and the ground pin, 你的 pin 角，你的金属角. Okay. Not only that, on chip, you need to lay out some of the capacitors and attach to your VDD9 and your ground 9. Okay? That is what I mean for such kind of on-chip decoupling capacitor. If you never do it, you can throw the ADC into the trash can. 你可以直接扔垃圾桶. I mean for high-speed operation or for high-end, high-accuracy ADC design. Forget about it. Even though you did a very good design and layout for your ADC, without such kind of decoupling, on-chip decoupling capacitor, you still cannot make it. Okay, only for very low-end applications, very low bit, or very low operation frequency, blah, blah, blah. That is not the usual case. Okay, so even for on-chip decoupling capacitor, you still need to make it. And this is the reason why you have a lot of details to take a good care. And not only for that, we have the other problem called bubble error. Bubble error means what? Yeah. For high accuracy one, the quantization level becomes smaller and smaller. Usually much smaller than VOS of your comparator. Okay? So what does it mean? All right. Allow me to zoom it for you. Oh, here I am in theory, and that is my top label by bottom label, but I have VOS. Okay? If it is negative, then for real comparison, it will look like this. If the VOS magnitude is too much, input offset voltage is too much, then the real threshold for comparison will below my neighbor. Okay? Or I get positive one. Oh, my real comparison, my real threshold voltage for comparison will be higher than my top label. So what is the consequence? Usually for such kind of comparison, flash voltage division, R string, we always hope you will get 0, 0, 0 all the way 0 and 1, 1, 1 all the way, right? You have a clear cut between your zeros and ones, but with input offset voltage for your comparators, especially for high accuracy ADC. Sorry for that. You have some zeros inside one, some one inside zero. That is the so-called bubble error. And how to remove such kind of bubble error? Because this is not a good representation for your digital signal. Yeah, to condense, to get better information density, we always have minorly weighted 二进位权重式的. Okay, this is no good. So this is the so-called thermometer code, 温标码. We need to convert it into minorly code. Okay? Yeah, we have the so-called priority encoder or decoder, 权重编码或解码器 priority. Okay, you just Google online, you will get the VHDL or very low code. You don't need to write it by yourself. But you need to make sure your input to such kind of priority encoder decoder look like this: all zeros and all ones, a clear cut. But usually after fabrication, you get bubble error, and the output for your priority decoder encoder will be incorrect. So you need to remove such kind of bubble error before priority decoder or encoder. Okay? How to make it? Yeah, that is the digital problem. Do it by yourself. With 3 input NAND gate, you can remove 1 bubble error. Oh, what do I mean? 0, 0, 1, 0, 1, 1, 1. Okay, only 1 bubble here. You can remove it through such kind of 3 input NAND gate. If you have more than 1 bubbles, okay, you need 4 input NAND gates. Blah, blah, blah. Okay, again, what is the operation principle? Oh, that is some kind of digital gate. That is idea. So read it, watch the circuit, and think by yourself. I'm your analog IC design teacher. Yeah. Again, I understand, but it takes a long time to explain. So do it by yourself. Yeah. Because usually it is harder to understand analog part instead of the digital part. Okay, so do it by yourself, because again, I cannot teach you everything for the class. And this is the other problem for kickback. All right, because we have such kind of comparator to be turned on, turned off. Such kind of turn on or turn off will propagate when we change our static comparator to a dynamic one. It means we need the help of clock to turn on or turn off some switches. But such kind of on-off switches, you will, during turn on, especially during turning off, you will get a lot of charge injection, clock whistle, blah, blah, blah. All those noises will propagate back to the input. So your input look like this. No, you will get a lot, a lot of kickback interference from the comparators. Your input get some error, some noise. Noise means error, right? Wow. It will hurt your angle, your effective number of bits for your final measurement. If your ADC works, you still need to face that kind of problem. So the fourth reason for preamplifier is it can help you to reduce the kickback signals. Okay, again, from output to input, you get some kind of attenuation instead of gain. Okay? Yeah, but even you have such kind of preamplifier, right? If you have no preamplifier, then it will cause some major errors for your measurement. But even you apply preamplifier, you can reduce it, but you still need to do your very best, especially according to your layout. That has better no coupling between the input to the output. Otherwise you still get some kind of interference. Okay. Anyway, I'm really happy to show you the fourth reason for preamplifier, and this is the reason why I warn you: don't believe everything you learned from the papers or from the textbooks. Sometimes they cheat you. Yeah. Where are the reference voltages? They never talk about it. They never do such kind of design on their own chip. All right. And sometimes they simplify the structure. Maybe they don't have space enough, because for the paper we have length limitation, usually for I3.4 paper, 8 pages. Beyond that, you need to pay for it. So they try to reduce. Sometimes they wouldn't like to cheat you, but they need to fit the page length. They need to simplify their circuit. But during simplification, you will miss a lot of details. Okay? So you need to pay attention to everything. Yeah? And this is some kind of circuit for you to refer. Anyway, how to do such kind of preamplifier, such kind of track and latch. Yeah, you can read it. You only need to, if you would like to do the design, okay, yeah, you only need to change the BJT into MOSFET. That is the easiest way for you. Okay? Anyway. All right. Allow me to finish the flash ADC, then we can have a break. Yeah, I need to take my coffee again. To improve the angle, you can do output averaging for your flash ADC. For what kind of output? Never mind for your comparator or for your preamplifiers. Okay? So allow me to show you this. Two ways to average the output. One is DC and the other one is AC. Okay? For DC, we do such kind of resistance averaging. Okay? Yeah, for the output, positive, negative, I don't care. Yeah, if you connect, that is the equivalent model. Okay, the real connection looks like this, but according to your small signal equilibrium, blah, 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 you get this. What I would like to say is, for example, if I'm larger than ideal value, okay, and you are smaller, then my output according to such kind of R later, okay, R later, my output will have impact of your output, and your output will have impact on my output. That's it. Okay. Okay. Equivalently, never mind that is current or voltage. I don't care. Okay, equivalently for each one to the other. Okay, you will have equivalent this and that, REQ2, REQ1. Okay, so my output will have impact on yours. Similarly, your output has similar impact on mine. And if you are lucky, no. If you pay attention to your layout pattern, 0, 1, 2, 3, you try to randomize the output of your current sources, your voltage sources, then congratulations, they are uncorrelated after fabrication. So the positive or negative deviation from the ideal value will be randomized. So again, if you are lucky, I'm positive, my neighbor are negative, bingo. We can help each other to push the final result as close to ideal values as possible. Again, you may challenge me. Hey, look, I'm positive, but my neighbors are all positive. The first explanation, the first hint for you is you don't do good layout effort, because you and your neighbors, they have some kind of correlation. Okay, you didn't randomize their layout pattern. That is your own fault from the very beginning. The second explanation is I did already for you moments ago. Even I'm positive, you are positive, but for both to get maximum value. No. So after such kind of averaging, we can still help each other to reduce from the peak value. Okay, maybe that is the peak, the maximum deviation for a single one. After such kind of averaging, I'm here, you are there. Congratulations. We help each other to the middle. Got it? I told you already, for neighbors to get the maximum here or the maximum there, the probability is 0. Okay? Without averaging, if I am here, I get the maximum angle or the maximum angle there. Nobody can help me. But through such kind of R-ladder, I will be pushed downward or pushed upward by my neighbors, because they more likely they don't have the same positive maximum or negative maximum. No. Okay? So after averaging, that is what the final result you can expect. For isolated one, for single ones without any averaging. Okay, I'm here, you are there. Sorry for that. What is done is done. After fabrication, I get the negative maximum. You get the positive maximum. It hurts our angle very much. But through such kind of averaging, you can see after simulation or measurement, I don't care. You can see the thicker line, that is the thin line, and the thick line, 粗的线条, is the final result after averaging. You can see the deviation from the ideal line for the thicker one, the final result is much better than the thin one without averaging. Averaging helps a lot. Okay, that's it. You can see my output is connected to all the others through such kind of R-ladder. 所以你可以看到透过这个阶梯电阻网路，每个人都会影响到其他人。Each node, each output will influence all the others. Okay, so we can get much better result, much better linearity than before. I mean, than without averaging. Okay, I do my best to explain the DC averaging. Okay, so similarly for AC, just think by yourself. According to equivalent model, you charge it the same thing. Similarly, so think it by yourself. Don't waste my time and your time. Okay, Finally, I would like to tell you, again, we are from a democratic country, so you can combine both of them. All right, resistor model for DC and capacitor for AC. You can apply both of them to get better result. Okay, yeah. Finally, according to statistical theory, the more to be average, the better you can get. And this, again, a very good theoretical explanation for this kind of oscillator or capacitor later. The more output involved in such kind of averaging, according to this theory, we call it large number rule or something, 大数法则. Okay? The more involved for averaging, you get smaller deviation. Congratulations. That's it. Okay? You can improve your DNL and then angle. Much better than before. But do you need to apply such kind of very complicated R later, C later for your ADC design? Not necessarily. It depends on how good you need for your ADC. Okay, again, that is for high-end, very high-end ADC design. Otherwise, usually we don't pay such kind of price for your chip design because it is really expensive. You need a lot of resistor, a lot of capacitor. And you can say, hey, I can reduce the overall cost by reduce the resistance. But by reducing resistance, it means what? You need to consume more power. More current will flow from my node to yours, right? So you can step chip area, but you need to expand. Yeah, you need to spend more power. And flash ADC, it is the most power consuming structure. 它是最浪费电的. If you apply such kind of low resistance oscillator, no, you will increase the power consumption too much. Okay, so nothing is free. You need to do trade-off. Okay, between this and that, 你必须做权衡轻重，有得必有失，有失必有得. Yeah, you need to think how much power, how much area, and how about the operation speed, blah, blah, blah. A lot of minor issues. No. I cannot say minor. A lot of major issues to consent to do such kind of trade-off. Okay, yeah. Finally, I finished the explanation for your flash ADC design. But it is too power consuming, too area consuming. Is there anything in between? I mean, yeah, maybe we can reduce the operation speed a little bit, but to save more power. Okay, so for the next structure, I would like to tell you interpolating ADC. But we can have a break right now.